Welcome to our last video series lecture for Calc 3. We're going to talk about Gauss's theorem and maybe do a few examples, just a few, and then we'll be done. Okay, so Gauss's theorem, it's printed on the screen, so I'm going to let you jot that down if you need to. Of course, there's conditions with Calc 3. I don't know why there wouldn't be, because that's all we do is check conditions. We don't really do any math. But anyway, one thing in here that's maybe new for us is this idea of a closed surface. And so we just see the definition below here too. So we say that a surface is closed if it does not have any boundary curve. So if we look at the boundary of the surface, that it is empty. And anyway, if we end up satisfying these criteria, so piecewise smooth, closed, orientable, unit normals pointing away from the surface, great, then we say that the surface or the vector surface integral is equal to a triple integral of the del operator dotted with the vector field. Okay. The only thing that's maybe new to us is this symbol of a circle through the vector or through the surface integral. And if you remember previously when we saw that when we made that loop, we saw it back when we were first studying I believe the divergence theorem, and that just meant it was a line integral. It was a single integral, a line integral over a closed curve. So really all this means is that we are doing the surface integral over a closed surface. And so something like something that would be closed, for example, might be like a solid hemisphere, something like this. Okay, and you can imagine, okay, we're just going to shade it in quickly, and we're going to call that closed. We all like coloring, right? So this is closed because it includes its boundary, so it's a solid. So this is I'll just write the word so we know this is a solid hemisphere. And so I would call this closed region because if I look at the boundary of it, it's actually the union of two surfaces. It would be the kind of outer shell of the hemisphere, okay, not including the lower disk, and then we would have the lower disk. Okay, so then I would need to smush them together to get the entire thing. Okay, and so certainly we would inherit, the different orientations, and then we would want to make sure it's oriented consistently like this. Let's see, actually I would need that going the other direction, wouldn't I? So that they cancel out. And I ended up orienting them the same way. But anyway, so you add these two together, and that would create the entire hemisphere. Okay, so that's the idea of Gauss's theorem. Is once we satisfy a bunch of criteria, we can say that the closed vector surface integral is the same as a triple integral of the del operator dotted with vector field. Okay, so here we go. Solid ball, K, and we have vector field, K. And now I want to compute this vector surface integral over closed region, and we do call it the flux. Okay, we saw that language before. Wonder where. Anyway, here's a little diagram. That's beautiful, I know. So let's just go through and check those conditions for this unit, or for this particular sphere. Okay, D is a bounded solid region. Yep. Boundary is finally many piecewise smooth curve. Yep. Oriented. Yep. Okay, so we do satisfy all the conditions, and so I'm just going to tell you on the test, on the final exam, make sure to check conditions. Okay, you will lose points if you don't, but anyway, we end up being able to do this, and we can do this quickly because if we look at the equivalent statement, it would be the triple integral over the region D, or over the surface D of f of the gradient or the del operator dot dot f dv. And when I do this, when I do the del operator, the only thing that I get, if you look at this, the only thing that has the components where we need it is this one. So when I do the derivative, this is just going to be, okay, d2 dv. And if you remember, okay, this is going to be 2 and then the triple integral of dv. Okay, and this, you might remember that this is just the volume of a sphere. So then we go back to high school geometry and say, okay, well, this is equal to 2 times, and then 4/3 pi, and then the r is 3 cubed, and we end up with 72 pi. All right, so just a quick example of Gauss's theorem. We'll get some more examples in the next video.